Hello, everyone. Tonight, let's begin with something simple: a quiet room, a gentle breath, and the strange fact that even in stillness, the universe is moving. Not with drama, not with noise, just with distance slowly changing its mind. If you could step outside the ordinary sense of time for a moment, you might notice that the night sky is not just a view, it is an archive. Light takes time to travel, so looking outward is also looking backward. And the deeper you look, the older the story becomes. This is a calm story about the beginning of the universe, not as an explosion you could hear, not as a fireball you could watch from a safe distance, but as a change in the state of everything, a universe that was once hotter and denser and has been expanding and cooling for a very long time. The name Big Bang arrived later, almost like a nickname that stuck. The reality behind it is quieter. It is a model, a framework, a way of explaining why the universe looks the way it does, using evidence that still surrounds us. So, slowly, let's follow the evidence the way you might follow a shoreline at night. You don't need to see the whole ocean, you just need to hear the rhythm of the waves. And the first wave is this: the universe is expanding. Imagine you are standing in a field after fresh snowfall, where every step is muffled and the world feels softened. You look around and everything seems still. Yet, in cosmology, stillness is rare. On the largest scales, space itself stretches. That idea sounds odd at first, because we're used to thinking of space as a container, like an empty room. But in modern physics, space is not merely where things happen. Space is part of the thing that happens. In Einstein's general relativity, space and time are woven together into space-time. Matter and energy shape it, and that shape guides motion. Space-time is not rigid. It can curve, and it can expand. So, how did we learn that the universe expands? We learned it through light. When light comes from a galaxy, it carries a pattern, like a barcode. Those patterns include spectral lines, signatures of elements and atoms. If a galaxy is moving away, the lines shift toward longer wavelengths, toward the red end of the spectrum. That shift is called redshift. At first, you might think redshift is simply motion, like the Doppler effect with sound. A siren approaches, its pitch rises, it recedes, its pitch falls. Light has a similar shift, but with wavelengths instead of pitch. In cosmology, redshift often means something deeper. It can reflect not just movement through space, but the stretching of space itself. As the universe expands, the wavelength of light traveling through it stretches too, lengthening gently, like a note held longer and longer until it becomes too low for a human ear to hear. When astronomers measured galaxies, they found a pattern. The farther away a galaxy is, the more its light is redshifted. On average, distant galaxies appear to be moving away faster. This is sometimes summarized in Hubble's law. Distance and recession speed are linked. It is an astonishing thought, and also a simple one. If everything is moving apart now, then in the past, everything was closer together. If you run the cosmic movie backward, distances shrink, galaxies approach, clusters compress, the universe becomes denser, hotter, more tightly packed. And when you follow that logic far enough back, you arrive at an early state unlike anything we see around us today. That early state is the heart of the Big Bang model. But science doesn't live on logic alone. It asks for fingerprints, and the universe, inconveniently for anyone hoping to keep its secrets, leaves fingerprints everywhere. To find the next one, we need to ask a gentle question. If the early universe was hotter, should there be any trace of that heat left now? Heat, in physics, is not only a sensation, it is energy in motion, and anything with temperature emits radiation. A warm object glows mostly in infrared. A very hot object glows in visible light. An extremely hot plasma glows in even higher energies. So, if the early universe was hot and dense, it should have been filled with radiation, not a few rays here and there. Radiation everywhere, in all directions, because the early universe would have been nearly uniform. As the universe expanded, that radiation would cool and stretch. Over billions of years, its wavelengths would lengthen. The glow would fade into a colder, lower energy form. And if that story is right, then today, the universe should still be filled with a faint afterglow coming from every direction with the signature of cooled thermal radiation. It sounds almost too neat, and yet it's real. The cosmic microwave background, the CMB, is a faint glow of microwaves that fills the sky. It was first detected in the 1960s, and its spectrum is remarkably close to a perfect blackbody, corresponding to about 2.7 Kelvin above absolute zero. It is hard to overstate how important this is. The CMB is not an artistic interpretation of the early universe. It is data. It is measured. It is mapped. It is a real signal that you can detect with the right equipment, even though your eyes cannot see it. If you could see microwaves as colors, the sky would never be dark. Every direction would glow softly, like a quiet fog of ancient light. And that light has a story. It comes from a time when the universe was about 380,000 years old. Not the first moment, but an early chapter. Before that, the universe was too hot for neutral atoms. Electrons and nuclei were separated in a plasma. Photons scattered constantly off free electrons, like trying to see through a dense storm of glitter. Then, as expansion cooled the cosmos, electrons could finally settle into orbits around nuclei. Neutral atoms formed. The universe became transparent. And the photons that had been trapped in constant scattering suddenly had a clear path. They began traveling freely, in straight lines through expanding space, cooling and stretching along the way. Those photons are still traveling. Some are arriving here, now, passing through you without harm, because microwaves are gentle at that temperature and intensity. So the universe is literally bathing in its own memory. Now, if you are listening to this while you drift toward sleep, there is something comforting in that. The biggest story we know is still physically present. It's not just in books, it's in the sky. And once you accept expansion and the afterglow, the mind naturally takes the next step. what was it like earlier, when everything was closer, hotter, denser? To answer that, we can walk down a timeline, but we'll do it the way a storyteller would, not by shouting dates, but by letting each era arrive when it's ready. In the beginning, the universe was not arranged the way it is now. There were no galaxies, no stars, no planets, no atoms. There was a state so hot that matter as we know it could not hold itself together. If that sentence feels slightly unreal, that's fine. The early universe is not built for intuition. It's built for equations. We'll translate the equations into calm images. When the universe is extremely hot, energy and matter become interchangeable in the way Einstein described with mass-energy equivalence. Energy can produce particle-antiparticle pairs. Particles can annihilate back into energy. In such conditions, the universe is a restless sea of interactions. It is not chaotic in the sense of random, without rules. It is busy, but lawful. As the universe expands, the temperature drops. The drop is not because the universe loses heat to anything outside. There is no known outside that acts like a refrigerator. The cooling happens because expansion spreads energy out. Wavelengths stretch. Momentum distributions shift. The average energy per particle decreases. End quote. Cooling is a kind of quiet generosity, the same total energy shared across more space. Somewhere in that early evolution, many cosmologists think something remarkable happened, something called inflation. Inflation is a hypothesis, not a fully proven fact, but it's a powerful idea because it helps explain several puzzles at once. The universe appears extremely uniform in temperature across vast regions of the sky, regions that, in a simple non-inflation picture, would not have had time to exchange information or energy at the speed of light. This is called the horizon problem. The universe also appears geometrically close to flat on large scales. That's not impossible without inflation, but inflation makes it natural by stretching space so much that curvature becomes hard to detect, like how a small patch of a large sphere looks flat if you stand close enough. Inflation also offers a beautiful mechanism for the origin of the tiny irregularities that later become galaxies, quantum fluctuations stretched to cosmic sizes. If inflation happened, it would have been a brief episode of extremely rapid expansion in the earliest fraction of a second, taking a tiny region and expanding it enormously. Even if you don't hold inflation as certain, the broad story remains: early expansion, cooling, and a universe that becomes structured over time. And now we arrive at one of the most satisfying parts of the Big Bang model, because it connects cosmic history to something you can hold in your hand, something as ordinary as an atom. In the first few minutes of the universe, nuclear reactions took place on a cosmic scale. This period is called Big Bang nucleosynthesis. The name sounds complicated, but the idea is simple. As the universe cooled enough for protons and neutrons to bind together, the first light nuclei formed, mostly hydrogen, which is essentially protons. A substantial amount of helium built from 2 protons and typically 2 neutrons. Small traces of deuterium, heavy hydrogen, tiny amounts of lithium. And then the process stopped, not because the universe got bored, but because it expanded and cooled too quickly for heavier elements to be built in abundance at that time. This is a critical point. The early universe was not a factory for everything. It made the simplest nuclei, then handed the rest of the periodic table to the stars. When we measure the primordial abundance of these light elements in old gas clouds, we find values that match the predictions of Big Bang nucleosynthesis. Within the uncertainties and with some ongoing puzzles in details like lithium, which remains an active area of research, the overall agreement is one of cosmology's quiet triumphs. It tells you that the Big Bang is not only a story about space, it is a story about chemistry. The hydrogen in water, the helium in balloons, the trace deuterium in the oceans all carry the imprint of an early universe that was hot enough to do nuclear physics everywhere. Now, after the first minutes, the universe enters a long middle stretch of its early life. For a long time, it is still hot enough that atoms cannot form. Electrons remain free. The cosmos is a glowing plasma, opaque to photons. Light cannot travel freely. It scatters again and again, like trying to cross a crowded room where everyone keeps gently bumping into you and turning you around. Then, after hundreds of thousands of years, the temperature drops enough for electrons to bind to nuclei. Neutral atoms appear. The universe becomes transparent. That moment releases the light we now see as the cosmic microwave background. And at that point, the universe becomes, in a sense, quieter, not less active, but less blinding. After recombination, there are atoms, mostly hydrogen and helium. There is radiation. There is dark matter, if our models are correct. There is expansion. There is gravity. But there are no stars yet. This period is often called the cosmic dark ages, not because anything is wrong, just because there are no luminous objects shining in the way we're used to. The universe is like a stage before the actors arrive, with the lights turned down. But gravity is working. Gravity is patient, and it never forgets a difference, however small. In the cosmic microwave background, we see tiny variations in temperature, tiny variations in density. Those variations are very small, about 1 part in 100,000, almost nothing. But almost nothing is enough if you give it hundreds of millions of years. Where density is slightly higher, gravity pulls a bit more. That extra pull gathers more matter, which increases density further, which increases gravitational pull further. This is how structure grows, not by sudden leaps, but by quiet feedback loops. Dark matter plays a central role here. It does not interact with light like normal matter does, so it can start clumping earlier, forming gravitational wells that ordinary gas later falls into. We don't know exactly what dark matter is made of. We infer it from its gravity. Galaxies rotate too fast to be held together by visible matter alone. Clusters bend light more than their visible mass can explain. The cosmic web structure fits a universe where most matter is unseen. So in this story, Dark matter is the invisible scaffolding of galaxies. And then, slowly, gas falls into these wells. It compresses, it heats, it cools by radiating, it fragments into clouds. The densest regions collapse, and the first stars ignite. The first stars were likely different from many stars today. They formed from primordial gas with almost no heavy elements, and heavy elements help cooling, which helps fragmentation, which shapes star formation. So the first stars may have been very massive, bright, and short-lived. They burned their fuel quickly, and then they died, often in powerful supernovae, scattering the first heavy elements into space. That step matters, because heavy elements are not just decoration. They change everything. Carbon, oxygen, silicon, iron. These elements allow for rocky planets. They allow for complex chemistry. They allow for biology, at least as we know it. So the universe's first minutes made hydrogen and helium, and the first stars began the long craft of making the rest. As generations of stars formed and died, galaxies assembled, not in a single neat formation, but through mergers and accretion, through gravity's slow choreography. The universe became structured on the largest scales into filaments and clusters, with vast voids between them. It is sometimes called the cosmic web, and that is not only poetic, it is a reasonably accurate description of the way matter distributes under gravity in an expanding universe. If you could step far outside and look at the universe as a whole, you might see something like a three-dimensional lacework, threads of galaxies spanning enormous distances. It is beautiful in a quiet way because it is the result of simple rules applied for a long time. Now, from this point, the story could become an ordinary astronomy story. Stars, galaxies, planets, life. But we're still telling a beginning story, and beginnings always raise deeper questions. The Big Bang model is strong, but it is not the final word on everything. It tells us that the universe expanded from a hotter, denser state. It tells us that the cosmic microwave background is the afterglow of a time when the universe became transparent. It tells us that the light elements formed early with predictable abundances. It tells us that the tiny early fluctuations grew into cosmic structure, but it does not fully answer what happened at the very first instant, or whether instant is even the right word. When we push the equations back toward extremely early times, general relativity suggests densities and curvatures that become infinite in a mathematical sense, a singularity. Many physicists interpret this not as a literal physical infinity, but as a sign that our theory is incomplete in that regime. It is like trying to use a map of city streets to navigate the bottom of the ocean. The map is excellent for its intended domain, but you are asking it to do something it was never built to do. At extremely high energies and densities, we expect quantum effects of gravity to matter. We do not yet have a complete, experimentally confirmed theory of quantum gravity. There are candidate frameworks, like string theory and loop quantum gravity and others, but no final consensus. So when someone asks what happened at time zero, the careful answer is that the Big Bang model describes the early hot universe from very early times onward, but the exact nature of the beginning in the ultimate sense, remains an open frontier. This is not a weakness of science. It is a normal feature of honest knowledge. Every map has an edge. And for a sleep-friendly story, there is something soothing about that edge. The universe is large enough to keep some mystery, even while it hands us so much evidence. Now, because we're telling this in a gentle narrative, let's pause on a metaphor, not as a replacement for physics, but as a soft handle you can hold while the ideas drift by. Imagine a loaf of raisin bread rising in an oven. As the dough expands, the raisins move farther apart. Each raisin sees other raisins receding. No raisin is the center. Expansion is happening everywhere in the dough. That's a common metaphor for cosmic expansion. It helps clarify one thing. The Big Bang is not a bomb that went off at a point in space. It is the expansion of space itself, at least in the simplest interpretation. But the metaphor has limits. The dough expands into the oven. The universe does not obviously expand into anything. In the standard cosmological model, space is all there is, at least all there is that physics meaningfully describes. So the universe expands, but not necessarily into an external container. This can feel uncomfortable to the mind, which loves containers and edges and outside places. But physics does not promise comfort. It promises coherence. And the coherent thing we observe is that distances between unbound galaxies increase over time, driven by the expansion of space. Now, expansion does something else that might seem surprising. It changes what we mean by the observable universe. Because the universe has a finite age and light travels at a finite speed, there is a limit to how far we can see. The observable universe is the region from which light has had time to reach us. That does not mean the universe ends there. It only means our view ends there. If you stand on a beach at night and see only as far as the faint light allows, the ocean does not end at the darkness. Your vision does. The universe is like that, except the darkness is time. We can see galaxies from when the universe was much younger. We can see the cosmic microwave background from when the universe was only 380,000 years old. We cannot see earlier than that with light, because the universe was opaque before recombination. But there are other messengers. Neutrinos, for instance, could carry information from earlier times because they interact very weakly and can travel through dense plasma more freely than photons. There should be a cosmic neutrino background, a relic similar in spirit to the CMB, but far harder to detect. Gravitational waves might carry information from even earlier processes, because gravity couples weakly and gravitational waves can pass through matter that would stop light. In principle, a background of primordial gravitational waves could be a direct whisper from the earliest moments, possibly even from inflation. Detecting those signals is extremely challenging. The universe is not handing out its secrets for free, but the fact that the signals are possible at all is remarkable. It means the early universe may be accessible not only in theory, but in observation, if technology becomes sensitive enough. Now, to keep this story steady, and calm. Let's gather the main evidence again, but as part of the narrative rather than a checklist. First, the galaxies are redshifted, and the redshift grows with distance, suggesting expansion. Second, the sky holds an ancient glow, the cosmic microwave background, with the thermal spectrum expected from a hot, early universe. Third, the universe contains light elements in proportions that match calculations from the first minutes of nuclear reactions. Fourth, the universe's structure, the cosmic web, matches a story where tiny early fluctuations grew under gravity in an expanding cosmos. These lines of evidence are independent, and yet they converge. That convergence is why cosmologists are confident that the universe was once hotter and denser, and that it expanded to become what we see. Now, there is one more twist that changes the emotional feel of the Big Bang story, and it is this. The universe's expansion is not only continuing, it is accelerating. This discovery came from observations of distant supernovae in the late 20th century, and it has been supported by other data, including the cosmic microwave background and the distribution of galaxies. Acceleration implies that something is pushing the expansion to speed up over time on the largest scales. We call this effect dark energy. Dark energy might be a cosmological constant, a property of space itself, a vacuum energy, or it might be something dynamic. We do not yet know, but it appears to dominate the universe's energy budget today. So the universe has a beginning story, but also a future story. Expansion will likely continue, and if dark energy remains similar, the universe may become more diffuse over time, with distant galaxies receding beyond our observable horizon. This is not a sad thought necessarily. It is a reminder that cosmology is about change, and change is the universe's most reliable habit. Now, because your channel is designed for sleep and relaxation, it can help to let the story become more intimate, not by leaving science behind, but by bringing it closer. Think of your own body for a moment. Most of the atoms in you are hydrogen, oxygen, carbon, nitrogen. Hydrogen's nucleus, a proton, is among the simplest things the early universe made in abundance. Helium also was made early. But carbon and oxygen, the atoms that give chemistry its richness, were made in stars. Iron in your blood comes from stellar furnaces and explosions. So, in a literal sense, you are connected to multiple eras of cosmic history. There is an early universe part of you and a stellar part of you. You carry both. And this makes the beginning of the universe feel less like an abstract event and more like ancestry. Now, because every good story has moments of uncertainty, let's speak softly about the open questions, not as problems, but as the places where the story is still being written. One open question is inflation. Inflation is compelling because it explains the smoothness of the universe and the origin of fluctuations, but it is still being tested. Different inflation models predict different patterns, and cosmologists look for signatures, like specific polarization features in the cosmic microwave background or primordial gravitational waves. Another open question is dark matter. We have strong evidence that it exists, but we have not directly detected the particles, if particles they are. experiments deep underground, experiments in space, and high-energy physics experiments all continue the search. Another open question is dark energy. We measure its effects, but its nature remains unknown. Is it constant? Is it evolving? Is it a sign that gravity behaves differently on cosmic scales? Is it vacuum energy? These are questions still alive in research. And then there is the deepest open question, the origin of the Big Bang itself, if that phrase is meaningful. Some models propose a bounce, a universe that contracted and then rebounded into expansion. Some propose a quantum creation, where classical time emerges from a more fundamental description. Some consider multiverse scenarios, where inflation occurs in many regions, creating many pocket universes with different properties. These ideas are not settled, and for bedtime science, we don't need to force certainty where nature has not provided it. Instead, we can hold the uncertainty gently. The Big Bang model is strong where it is tested, and open where it is not. That balance is not weakness, it is strength with honesty. Now let's do something very simple and very calm. Let's take the timeline and walk through it as if we are moving through rooms in a quiet museum. The first room is the early hot universe, where everything is too energetic for atoms. Particles and radiation interact constantly. The laws of physics are present, but the conditions are extreme. The next room is the first few minutes, where the light nuclei form. Hydrogen and helium appear in the ratios that will shape the chemistry of the cosmos. The next room is the long plasma era, where light is trapped in constant scattering. The universe is luminous, but opaque. The next room is recombination, when neutral atoms form and the universe becomes transparent, releasing the ancient photons we now detect as the cosmic microwave background. The next room is the Dark Ages, when matter slowly gathers, but there are still no stars. The next room is first light, the first stars igniting, burning fast, enriching space with heavy elements. The next room is galaxy formation and the cosmic web, with clusters and filaments and voids like quiet pauses between threads. And in later rooms, billions of years later, planets form, chemistry grows intricate, and in at least one corner, consciousness appears, curious enough to look back. In this museum, you are not separate from the exhibits. You are part of them. Now, there is a subtle point that often gets lost in popular retellings of the Big Bang, and it's worth placing gently into the story because it helps keep the mind relaxed. The Big Bang model does not claim, in its basic form, the universe came from nothing. It says the universe was once in a hot, dense state and expanded. The concept of nothing is slippery. In physics, a vacuum is not necessarily nothing. Quantum fields can exist in vacuum states, and those states can have structure and fluctuations. So when people say something came from nothing, that might be a philosophical claim or a speculative physical model, but it is not the most careful way to describe the standard cosmological picture. A more careful way is quieter. We have strong evidence for an early, hot, dense phase, and the deeper origin remains an open question. That sentence doesn't try to win an argument. It tries to be true. Now, to keep you in the story, let's imagine a small thought experiment, one that brings the cosmic microwave background closer to your experience. Imagine you are floating in intergalactic space, far from stars, far from dust, far from the bright noise of galaxies. So, you turn in a slow circle. In every direction, there is a faint microwave glow. It is almost perfectly uniform, as if the universe remembers a time when it was smoother than it is now. But it is not perfectly uniform. There are tiny variations, tiny ripples. Those ripples are not errors. They are the beginning of structure. They are like the faintest wrinkles in a sheet that later becomes folded into mountains and valleys. Gravity takes those wrinkles and, over time, turns them into galaxies, clusters, and the cosmic web. So the CMB is not only an afterglow, it is also a blueprint, a soft one, a blueprint written in temperature variations so small you could miss them if you blinked, if blinking mattered to a telescope. Now, let's bring in another quiet tool of cosmology, the idea of scale. The universe is enormous, but the laws that shaped it are often simple. Expansion cools. Gravity amplifies density differences. Radiation carries information. Particles interact according to known forces. In a way, the Big Bang story is not complicated because the rules are complicated. It is complicated because the time spans and distances are huge, and because our brains did not evolve to feel comfortable with billions of years. But you don't need to feel comfortable. You only need to float through the story. And the story has a steady rhythm, hot to cool, dense to diffuse, uniform to structured, simple to complex. Now, there is a gentle irony here, and it's worth a small smile. The early universe was simpler in structure, more uniform, more symmetric, and yet it required some of the most advanced physics to describe. Meanwhile, the late universe is messier, full of complex structures and life and weather and opinions. But it follows from the early simplicity through time and gravity and chemistry. So, complexity is not always the beginning. Sometimes complexity is what happens when simple rules are allowed to run for a very long time. Now, if you are still awake enough to enjoy one more clear clarification, here it is. When cosmologists speak about the Big Bang, they are not saying that all matter was once squeezed into a point in ordinary space, sitting somewhere inside a larger emptiness. They are describing a state of the universe where the scale factor, a measure of cosmic size in the equations, was much smaller, and where density and temperature were much higher. The point idea often comes from pushing the equations beyond their tested domain. In reality, the earliest times we can describe with confidence are extremely early, but not necessarily a literal point of infinite density. The universe may have had a minimum size, or it may have had a quantum description, where classical size is not defined the way we imagine. Again, this is not a flaw. This is the boundary between what we know and what we are learning. Now we can let the narrative soften again, because sleep likes softness. Think about expansion one more time, but not as a math curve, as a feeling. Imagine distance itself slowly relaxing, like fabric gently unwrinkling. Galaxies are not actively trying to flee each other like anxious birds. Most galaxies are held in groups and clusters by gravity. Within a galaxy, stars orbit and remain bound. Expansion is most noticeable across the vast spaces between galaxy clusters, where gravity is not strong enough to fully resist the stretching of space. So the universe expands, but it does so in a way that respects local bonds. This makes the universe feel less like a bomb and more like a breath. A long breath, not one inhale and exhale, but a steady unfolding. Now, there is a question that sometimes appears at this point, like a curious thought tapping gently at the door. If the universe expanded from a hot, dense state, what determined the specific patterns we see today? Why does the universe have this particular amount of matter? Why this particular level of fluctuations? Why these constants of nature? Some answers may lie in fundamental physics. Some may lie in selection effects. Some may lie in deeper theories, not yet known. But cosmology has a practical approach. It measures, it models, it tests. It compares the predicted cosmic microwave background pattern to what satellites observe. It compares predicted element abundances to what astronomers measure. It simulates structure formation with and without dark matter and sees which matches reality. So even when deeper why questions remain open, the how questions are treated with serious, careful methods. And those methods have produced a coherent picture, one that has survived many attempts to break it. Now, let's return to the earliest moments one more time, not to force a final answer, but to place a gentle frame around the mystery. The universe has an age, about 13.8 billion years, based on multiple measurements. That is not a perfectly exact number, but it is well supported. If you rewind time toward the beginning, densities rise, temperatures rise, and our theories begin to strain. At some extremely early time, perhaps around the Planck time, roughly seconds, quantum gravity effects likely become important. That is an unimaginably small fraction of a second. At that scale, our everyday notion of time may not apply. Space-time may have quantum properties. The idea of before may lose its meaning. So, rather than picturing a firecracker at time zero, it may be better to picture a dawn where the concept of time itself becomes clearer as the universe evolves. Not a moment you can point to with a finger, but a regime change. This is speculative, but it is a healthy speculation because it acknowledges the limits of our current descriptions. And acknowledging limits is a kind of intellectual relaxation. Now, to keep this as a bedtime script, we'll let the story drift toward a calmer close, like a telescope slowly panning away from details and back to the wide sky. The Big Bang model is, at its core, a story about change. A universe that expands. A universe that cools. A universe that transitions from plasma to atoms. A universe that turns tiny ripples into galaxies. A universe that makes simple elements early and complex elements later in stars. A universe whose earliest light is still present. A universe whose largest scale behavior is shaped by dark matter and dark energy. Mysteries that are not empty gaps, but active research frontiers. And because it is bedtime, we can say this in the quietest, simplest way. You are inside a universe with a long memory. The light that fills space remembers a time before stars. The hydrogen in water remembers the first minutes. The carbon in living things remembers ancient stellar cores. And the expansion remembers, in its own geometric way, that the universe used to be smaller. If you hold all of that at once, it might feel heavy. So you don't have to. You can hold only one calm thought, that the universe has a story, and it is still unfolding, not with urgency, not with noise, just with time. And as you rest, the cosmos continues its gentle work. Space stretches, radiation travels, gravity gathers, stars burn, and the faint afterglow of the early universe keeps drifting through the dark, arriving everywhere, evenly, quietly, like a whisper that never learned how to stop. If sleep comes now, it will not interrupt the story. It will simply place you back into it, because you are not watching the universe from outside. You are part of the same expansion, the same chemistry, the same long chain of cause and consequence that began in a hot, dense early state and cooled into a sky full of structure. And tonight, that is enough. The universe was once hotter and smaller. It expanded. It cooled. It made the first elements. It released its ancient light. It built galaxies. It built stars. It built the ingredients for planets. And eventually, it built a listener in a quiet room, hearing the beginning as a bedtime story. So the beginning is not only behind you. In a subtle way, it is around you, in the background glow, in the atoms, in the distances between galaxies, in the simple fact that the cosmos, even now, is still becoming. Rest. Keep it gentle. Let the biggest story in science be, for a moment, not something to solve, but something to float in. Because the universe does not demand that you understand it tonight. It only continues patiently while you sleep.